product innovation and all the teaching facilities. We really witnessed that, and so happy to welcome you here. And looking forward into the possibility of the collaboration for the joint partnership, joint publication, and also some of the possibility schemes. Actually, the visit at this time, the directors from Tunghai wish to visit the main office in UGM. Then I contacted the IC. Would it be possible to have this kind of session for the public lecture for us to get to know, to understand more about the recent development, about the knowledge that is related as well, very closely to us. So, the Professor Huang, and also Professor Ng, also Professor Tuan, said yes to the request. So we're so happy. And another happiness that we received during the lunch discussion is that we welcome possibilities of having the joint MOOC. We can send videos to, update about the recent development, the recent advancement of the technology in terms of AI and the like. We are also encouraged by our by our rector of UGM to have the MOOC. And as you can see here, our colleagues, they are also very strong expertise. Pak Ganjar, 2% scientists in the world, very strong in the innovation as well. So hopefully that we can, learn one another, and hopefully that there will be a collaboration that we can run after this. So again, thank you so much for your willingness to share with us today. Again, welcome to UGM and all the colleagues here and all students who happen to come. Please welcome Professor and learn something from them. Thank you so much.
Thank you so much, Dr. Ng, for the welcoming speech. So we would like to start our lecture session. So today we will separate the lecture into two sessions. So first session will be delivered by Professor Huang-Nan. The topic is from mathematics to data analytics to AI, turning numbers into intelligence. So we would like to start now. So we will not wait for the time, so we'll do this. We let Professor Wang to start. Time is yours.
Okay. Since the presentation of IST,
I'm sorry. Excuse me. Microphone.
Put it here.
Yes.
Okay. Let me talk these topics. Okay. So before I talk, I should mention my undergraduate is not mathematics. I am aeronautic and astronautic from the National Kwai-Kong University in Taiwan. So I got my undergraduate and master degree there. And then I worked in maybe the military department for 6 years, and then come back to the PhD in applied mathematics. Okay, so maybe sometimes, for example, yesterday I met the head of the mechanical engineering. Yeah, we can have some kind of common knowledge because my undergraduate training. Okay, so today I would like to let us think about. So because from mathematics to data science and AI, which is the way we want to turn the number, transform the number to be intelligent. Okay. My talk can be consist of the 4 parts. Okay, so I will introduce it in this way. I will not go into detail for each item. So we may ask why I say AI is everywhere. For example, this form is more powerful than the computer I use to generate my master thesis. Sorry, I'm doing the computation of external aerodynamic field. So I use lots of computer, but no, this one is much stronger than that time's computer. Okay, those things change. So from the smartphone, YouTube, Netflix, even maybe 5 or 10 years later, we can go home by calling car, self-driving car. Okay, and then how about healthcare? So all these systems actually equipped with a large database and many machine learning models with optimization. Okay. For example, if we say YouTube use AI, why? YouTube, you look at what video you watch. Okay. I think many people use the short in YouTube. Yeah, what video you do, and how do you watch them? What do you like or skip? What similar users watch, and more other parameters. So they all turn into numbers. Okay. So the YouTube want to do things. YouTube want to predict which movie for you is you will like next. So what is the mathematics inside? So we can say, actually, YouTube collect those number, watch time, click history, like, such word is numerical data. So it got a lot of numerical data. And based on mathematics, what is the mathematics used for? We like to find the trend, like the pattern. So maybe use probability theory, linear algebra optimization. So you will find some relations between data. Okay, movie A may be related to movie B or movie C. So they will find this information. So, and then we will go to the AI. AI means predict for each watcher. When we watch the YouTube, okay, you are based on my use, my experience, and use so-called metric factorization optimization to predict which movie you like next. So actually, you can say YouTube is just a very smart TV guide for us. I don't know, do you remember, if you watch some specified movie, and then next time it will promote that for you, yeah. And sometimes it promote the other side for you. So it is use AI inside. So based on this, we can consider we use everywhere. We use AI, okay. And we can think about everything is a number. I learned this word from the age of about 30 years old. I read something, it's written, everything is a number, okay, from some religion. Okay. So here, I just use a simple example. So let me try here. So it's a sound, yeah. Actually, if I take the amplitude, you see this is the product of the amplitude. So when you turn into amplitude and the phase, just numbers, okay. And this part is the Chinese character or Tunghai sound, yeah. This Chinese character for Tunghai sound. So I use this as some kind of one-dimensional signal. So for the image, for image here, if I have cursor here, you see, and I have a small rectangular, so the value is shown here. For example, here it says red color is 247, green is 64, and blue is 56. So which means this is a matrix but with three divisions. So we can consider like a tensor. So we turn the image also into numbers. Okay. And furthermore, for us, I think everybody will go to hospital. Do you know your friend never go to hospital? It's very seldom, yeah. So when we go to hospital, you see each row is your record. The first one may be the number, the birthday, yeah, and the gender, and then so you have many features for you. For example, this was the area of left ventricle, okay, the white, okay. So this is a feature, but each time when you go to see a doctor, you just have a record. So for each record is a person, yeah. So we can say people turn into a table. So do you believe me? Everything is a number. So we cannot get away from number. For example, we are getting old, yeah. We are getting getting more money in our pocket. Yeah, so it's become a number. Yeah, if you have so many money, you cannot use it in your life. So it's just a number. Yeah. So here, what is the math used for? We think math just wants to find a pattern. Maybe from three perspectives. The first perspective, we can say we use statistics to look at the data. Okay, so you may say I calculate the mean, the variance, and the correlation. Actually, you want to find a pattern or trend. That's statistics. Okay, but besides, we may go further. We want to see the trend. So we will say how one variable affects another. So maybe we will suggest a linear equation or polynomial equation, even exponential or logarithmic function for it. So the purpose is a little bit different. This is try to find trend. This one try to predict for the future. So regression try to predict. Okay, but some of the data is not obviously to look at their relationship. Then we can say we can use clustering. So clustering will use some technique that can mean they can group similar data together. We can say this is a group, this is another group. So it's very, very useful for medical health. Yeah, when you come in, you have some many physiology measurement. When I say you belong to this group or this group, I can use different treatment. Okay, so you can see math find pattern in these three ways. Okay, one further. And the last one is belong to the AI. Yeah. Okay. So I give a example from my calculus book. Okay, the calculus book, the number is from 1989 to 2001. The test of ARDS in US. Okay. So as you see, the number quite increased during 1993. 1992, 1993, 1994, 1995, and then reduced so quickly. Okay, that's because some of medicine has been found, but actually it is not. Okay, so the green dot here is to indicate the number, will be then the number. Okay, suppose we use the cubic square fitting, so we will find this red line, and we want to predict what is the number for May 2002 based on this line. Okay. So this is the traditional mathematical way. We teach students to do this in undergraduate. They can do it, okay? But now we are using the so-called neural network. So this year I have a tip student who is come from Indonesia to my place for 4 months, and I asked her to do this project using neural network to review this data, okay? Actually, we can find we can separate to two types. Okay, this type is for image. Yeah, you look at that. So convolution neural network. This type can deal with, we just mentioned, maybe even one-dimensional, two-dimensional data. You can use this way. So the X is called input, the U is called output here. So each one is a neuron. Okay, so if we looking into that one, this is a very similar, very simple one. It's called single layer with 3 neurons. Yeah. You see, it gets one input and produces one output. But for the hidden layer, each has activation function like this one. So we collect all those weights as a matrix W and all those pairs as vector B. So we can do this kind of computation to get a prediction. Okay. So basically, we can consider neural network just, let me see. Consider just neural network just as a layer of function stack, a layer of function stacking. Okay. So in here, as I just mentioned, the student went to my place. I let him do this project. So for example, we have 2 layers, each has 6 neurons, and then we do the computation for the same database. You see, the prediction is so good. You see, it's a smooth curve. Yeah, almost pass through this measurement, and then we can do further for prediction. Okay, it's quite different from previous. We use just mathematics. Okay, so neuron has so strong capability. So once you get into the neuron, okay, you will ask the foreign problem, how the AI learns. Okay, so we have neural network there. We have some input. We can get output. So we are saying the AI can learn by making a prediction first. Because initially you have weight, you have bias, so you can compute the prediction. But prediction is not correct. So you will make an error here. So the AI, they always say, I predict your behavior, or it's not correct. Maybe I can reduce the error, okay, in this way. And I adjust myself to reduce the error, okay, step by step. And the second step, how to reduce the error. Maybe we sometimes use the gradient descent, which means you can go like when you climb to the mountain, you want to go to downhill, the lowest point. So you will adjust it. So you adjust according to the gradient, gradient of the error, okay, and then adjust the weight. So here theta means the weight. The weight is what? Remember, this is the weight, the weight here for each line, the weight, and this is the weight in the bias. So you just change the number. So eventually you will get a correct weight, a correct number, but it is not, maybe not unique, okay. So we call this as optimizer. So gradient descent is one type of optimizer. So there are many optimizers here. So actually we can use this small picture to capture what we just talked about, okay? We construct a neural network, we do the forward pass to predict the value, and then we compute the error, loss is error. And then if the error is small enough, we say, okay, if it is enough, we go back to update the theta, the weight, and the bias. We call it backward pass. So it's forward, backward, it's an iteration process. Redo and redo again, okay? So you start, and end, you get a complete flowchart in this way. So I let the students to study different architecture, maybe 1 hidden layer, 2, 3, 4, or 5. I would see what is the effect, okay? And the next, I would like to say, we have learning rate, because we are just, I just here, this is called the learning rate, This is the gradient, okay? Gradient means the lowest, try to reach the lowest point. But you can have a ratio here. How fast 1, 2, or 0.1 is this part. We call the learning rate. So actually, when we do this problem, the learning rate do affect. You see, different learning rate, the convergence speed is different. So learning rate affect that. So we combine to say, for different activation function, I just show about tangent. Actually, we have relu and sigma. The results are different. For different learning rate, this is 0.01, 0.01, 0.01, and 0.1. You see 0.1 is quite good, Here is not the true value of the output. We just compute the output at this point. Okay, actually it's a smooth curve, We just compute the output at this point. It looks like this. So we say, so from this way you can study very kind of parameter affect your neural network. But it's not enough for us, because when we're doing real object, for example, you are simulating a car. Car has an equation of motion, Okay, you are doing a fluid mechanics, it has equation of motion. So here, excuse me, I use many Chinese inside. Okay. So we can consider if we have a mechanical system moving here. Okay, actually physics tells us it should be covered by this equation. Okay, maybe m mu k is unknown, maybe known. Okay, and this way we can do some measurement, so we can have data. So then we can combine these two into using neural network. Okay, so I'm thinking what is so-called physical informed neural network? It's just neural network plus physical information. Here we call equations, initial conditions, boundary conditions, and some energy function. We call it physical. So we combine these two together. Okay. So I give you a very simple example here. I do not have so many mathematical formulas. I know many parties do not like mathematics too much here. So here, this is just for ODE. We just mentioned, this is the second order ODE. This is initial condition. So I did not, we have data here. So when you have the predefined weight and bias here, and then you compute the output and use the so-called auto differentiation, you can find a derivative. You don't need to pay. We already checked it. It's almost exact derivative, almost exact as you do by hand. So it's quite strong, very nice algorithm. So we can compute the y derivative, second derivative, first derivative, and then you add it. It may be zero, maybe not. So we call it as loss of equation. And here is initial condition. You will check from the neuron, you can compute the value at zero and its derivative at zero. Is this equal or not? You can say it's a lost. Actually, you can have some measurement. So your real data is here. And then coming in. So we try to use the, I just mentioned backward pass, yeah, to calculate the theta to minimize the error. Okay. Once you calculate and then you update the network, you will produce a new result. So it's a cycle until the loss is less than your tolerance is get out. Okay. So I show you a very simple example here. Here, one dimension, only one variable, yeah, simple, and one derivative. Okay. So the equation is here. The exact solution here, okay, I just use the neural network. Actually, it takes about 100 iterations. It's strange. And you see, actually, you cannot make difference by your eye, yeah. But I enlarge the differences here. The largest difference in the boundary, because we just compute from 0 to 1, yeah. The boundary has the biggest error, but actually, the other part is quite small. So, in this way, you can treat differential equation with a neural network, not just by formula. And we can add data in. Don't forget, we can add data in. So if the coefficient here, if the coefficient here you are unknown, yeah, you can say, for example, I'm thinking m is a unknown value. I can say I can add one output here and put it here. So you can identify what is the number for m because you have data here. So it's very easy to apply to real problem. One of my friends in National Zhongxin University, as I told him this idea, he already made a real machine, use this way for help you to train your arm or leg. Okay, and then he told me his student come to a board for competition, maybe the number one. Well, use this, it's so maybe 2 or 3 months, you finish that. Oh yeah, real application of this. Okay. So from here, we can say mathematics is important, but when you learn very difficult things in mathematics, now the computation we can use neural network to help you. Okay, and the procedure, the process is almost the same. Okay, from here, I would like to give 3 examples of my work. This is more from 2019, okay. Because it's quite early age in AI, so the method is quite old. Already belong to machine learning, it's quite old method, okay. So if you have a picture for diabetic foot patient, okay, you have a picture. You want to determine how large is the wall in area, in perimeter, okay, to do things. So we take the picture, we use a lot of technique, and then finally we segment the wall, okay? But another thing, because we have different camera or different mobile phone, we take different perspective. So they will not be parallel to here. So we design a label here, okay? Okay, and then based on the label we obtained, we try to construct some transformation, matrix transformation. So we try to transform the label here to be correctly expand to 4 direction, to be right rectangular. Okay, and once I determine the transformation matrix, I map this back to here. So this should be parallel to the wall, yeah, in general. And from here, I calculate the area and perimeter from here. So I use many mathematics inside, but actually I just use the image processing, which is called segmentation. Yeah. So this is the first job. And the second job, we have a lot of ultrasound data for people with aortic stenosis problem. Okay, we want to talk about what kind of treatment is best for the patient. So actually, you see, there are so many features recorded, at least 23 features. So the meaning of feature can be look at ultrasound picture here. Okay, so our target is to say, is the data really in the dimension of 23? No, actually not. When we do our data analysis, we really find 7, 8, 9 is enough to represent 90% of the phenomena, which means the actual dimension may be less than 10. So many of them may be combined by the other dimension. So actually the data is not really so complicated. So based on those more important features, so maybe we can design a very quick examination way to check about the patient. Yeah, we don't check so many parameters. So which means maybe we can come down to so-called edge computing. We don't need so large computer. Okay. The third one, I done this last year. It's for ulcerative colitis. It's quite, this disease is increasing nowadays, and even for young people. And the bad news, it will not totally recover. It's just severe or mild or almost good. Okay, almost good. So the teacher, some of the professor from the other department asked me to help them because they are doing the drug development. They want to check is the drug effective or not. So actually this is just the first step. So we based on the endoscope to do this kind of analysis. We would like to say if you give me the endoscope in DICOM format, I would like to judge is it's quite good or only a little bit or mild or very severe. We would like to distinguish that because for each patient, it may contain at least 50 pictures there. So sometimes the doctor or the physiologist cannot inspect very detailed. So we try to develop this one. Actually, we will finish the first stage, but we achieved the accuracy only about 90%. And the professor said maybe it is not enough for 90, maybe he lacks 95. So our training is based on the public data set. We build a model, and now we try to look at another big data set. And then we will use some data from the hospital for double check for this one. So we are still doing this way, okay. So from here we can think, actually we can consider AI in this way. If you are cooking in your home, yeah, we can see data is so integrated. And the math like a cooking recipe, and then AI is final dish, okay. And what is the model, which means brand? How to cook, yeah, use your brand. And training means practice, yeah. And the error means mistake. And great is making working down here. And actually neural work you can consider as a factory. So we can have a more academic terminology. Actually, it's just like our everyday life. Okay. So what is the skill for the future? I think this is quite important for students. We can train them with mathematical thinking. Okay, although we are not training them to be a mathematician, but they still must know some mathematics. For example, probability, calculus, stochastic, or some of behavior like stochastic, yeah, maybe optimization. So they should learn. Okay, besides, okay. The other way, they need to have a very strong capability in coding. Nowadays, we use Python, yeah. In my department, although we are math department, we teach Python over 10 years. So 10 years ago, we switched from C++ into Python. Students appreciate it. Nowadays, we prove our strategy is correct, yeah, because we just fit in the AI. Okay. And the last one is data thinking. As I just mentioned, yeah, some one-dimensional signal. Stock market, yeah, last night, American stock market grows, yeah, goes back again, yeah. So every day I will look at TSMC. If TSMC is grows, Taiwan market is grows. If TSMC is down, Taiwan market is down. Okay, so it's some kind of time series, also one-dimensional cycle. And we take picture here, is two-dimensional cycle. Okay, sometimes we have 3D information. For example, you go to the hospital, say, I will do some MRI, it's 3D information, it's just a number. Okay, so we need to train in data with students have data thinking. Okay, it's quite important. When I did not mention when we work this data, I ask a student go to hospital to spend 3 months to review the data. At the end, I get nothing. Because the data is so dirty, you cannot use it. But yeah, actually, you spend 3 months, get nothing back. Okay. So I do it just based on the data provided by doctor himself. I did not use, originally I would like to add more data, but sometimes it's quite difficult. So data thinking is important. Not the data you get is correct. You must remember. So much of time you will spend in correct the data, find the error, and make the data useful. So you must ask students to think about data. Okay. I think these 3 parts you can organize the student, which combine, turn them to be data scientists or AI engineer. It's quite important. So here, actually, math is important because math can transfer the data to be intelligent, can tell you the story behind the data. Okay, it's quite important. In Chinese, we have some kind of 相命, you know? To look at the face and use your face. Yeah, it's the data. They are training to read the data from your face. Yeah. So I think that spatial data we are not easy to obtain, but math is more easy. Yeah, from the internet, from YouTube, from ChatGPT, you can get many support. So actually, math can transfer data into intelligence. So let's conclude my talk. Yeah, this picture, that's from my office, to the central mountain, Taiwan. Yeah, I'm the 6th floor, 6th floor. Yeah, so I look at this one. Yeah, if the weather is bad, okay, you cannot see the mountain. If weather is nice, you can see the mountain and the full city. Okay. So thank you so much. So maybe we can discuss later.
Okay, so thank you so much for the really interesting presentation, Professor. So by the presentation, we can conclude that everything in this world actually is a mathematics, everything is the data, and we can do the analysis and then improve it into AI or artificial intelligence. Yeah. Okay, so now is the time for the question and answer. So I would like to, since the time is very limited, I would like to open 3 questions from the audience.
Wow.
So if you have any question, please raise your hand so I can give you the microphone. Thank you.
Because my undergraduate was not mathematician. So yeah? Yeah, no problem.
Great. Thank you very much, Prof, for giving us the lecture. It was nice. I think you have a lot of experience.
No, sit down.
Okay, yeah. A lot of experience. You show us some application of AI, especially neural network and other machine learning. We have 2 questions actually. The first one is that because most of us here is coming from vocational college,
yes,
which means all of our research must be, produced as a product or software that can be used by the society.
Yeah, I agree.
And I think that was a very hard task
Yeah.
Because once we finish our research, the next problem is that how this
That needs to be
result
true.
can be used, right?
Yeah.
And maybe you can give us some example, because you are doing in the healthcare area. It means usually it's very difficult for clinical trial and how to make sure that your research can be developed into product and that can be used by people. Maybe you can share to us some experience that you have done in Taiwan, so we can learn from it. Thank you, Prof.
Okay, I just mentioned about the PINN, yeah? PINN, Physical Informed Neural Network. So one of the colleagues in National Tunghai University turned into the real product. For example, we have 3 motors here, they combine into one set, and they measure their movement. Okay, they measure their movement and build the model. The model is not built by hand, by mathematics, by measurement, but direct by the data. Once they build the model, they use the control strategy we already know, yeah, to design the PID control. And actually, it's doing very good in, for example, if I put my hand there, it can move in a circle or an infinity shape or triangular shape, which means to train the arm. Some people, because maybe the arm is hurt, yeah, so they can help them to train. It's so quick, so it's one example for you, okay. And the other, for ultrasound data, we work with the doctor, okay. Once we design our algorithm, we'll go to the hospital, and then we are not built on their central system, on another small machine. Okay, and the new data coming in, this data will reproduce some signal for the doctor, can help him to make some decision. Okay, for example, is this pill coming in, it needs to take egg or surgery or just wait to die. It's actually the case. Yeah. And it's not easy to predict the future behavior, because many patients come to this hospital maybe 1 or 2 times and leave. So it's very not easy to do the prediction. But actually for the new coming data, we can really, based on the model, to help them to do some assistance. You cannot replace the doctor, but assist them there. It's really reliable. And the third one, we will try to, because we are still developing, we will try to create software, maybe like the APP, yeah, to read the data directly for the doctor to use. Maybe we can talk about later. Yeah. Okay.
Thank you. Probably one more question from the audience. Yeah.
Please.
Please, Dr. Prof.
Thank you very much, Professor.
You're
My
welcome.
name is Prof.
Okay.
Your lecture is very interesting, and I'm also interested with that lecture. You, Professor, working with the data. Of course, we need the valid data. And as well, in order to provide the valid data, we need an equipment, we need an instrument.
Yes.
That
Yes.
provide that one.
Yeah.
Especially for the medical purposes. It's
Yes.
very working with the small signal, which
Yeah.
is less than the noise.
Yeah.
And based on your experience, any scenario that you have built in your research to incorporate any other discipline or interdiscipline with the other department in order to provide the good research result. Thank you very much.
Actually, my research type has many aspects. Initially, I was a control engineering, okay, and I doing some control theory. And later on, I think if I pay so many times to teach the student, even 2 years, they cannot do my topics. So I try to do the signal analysis. So I send students to learn how to do the signal analysis. Okay. And as you just mentioned, mostly I work with the IT department. Okay, yeah, computer science. I work with them. Okay, so sometimes I got the data from the doctor. Yeah, okay, I got the data. Or some Yeah, we got the data, and we sometimes ask doctor to teach our students. For example, there are so many pictures, yeah. So how to read the picture, or how to judge this is what kind of disease, yeah. So the doctor is not have so many time to do the labeling. You must ask your student to do the labeling. So they will teach us how to do the labeling. And students do the labeling, and then we put it into the computer to do that. So actually, you are mentioned quite right. If the sensor is not good, yeah. If the people, the technician operates not correctly, it's make bad data. So you cannot use it. It's really true. But nowadays, many instruments are made by big companies. They always build many filters inside the machine. So now we get the data is really clean. Sometimes, yeah, it's better than earlier days. So the problem is reducing. So we just talk about how to clean the data, the effort may be less for new coming machine. Yeah, we can believe that. But actually, I cannot do it by myself because I stay in math department. Okay, only 1 or 2 students can help me, not in general. And also in our department, we do another aspect we call dementia. We use AI to predict dementia on questionnaire and also by MRI. We're doing this kind of research in another. So we have many applications in medical image and medical signal processing. Okay. So maybe you can help us to, from the real aspect, yeah, how to read the data, yeah, how to treat, how to transform. Some data coming in, you already be transformed by Fourier transform, yeah, you must transform it back. Okay. Thank you.
Thank you. So yeah, this is the last session for the first lecture. So we would like to move to the next session. So please welcome Professor Kwai-Kong. So we will talk about how machine learning finds hidden things in matter using AI to detect the transient. So please welcome Professor Kwai-Kong with the big applause.
Thank you. Before I start, I really have to thanks for the. Oh, sorry.
Yes, I'm sorry.
Okay, thank you. Yeah, thanks for the department for inviting us so that we can visit this university again. Actually, I have came here 8 years ago. Okay, this is my first. This is my second time, and we really appreciate very much. This is a very beautiful campus, and especially all the beautiful people here. Okay, yeah. Okay, I'm really glad I can share with some of my work here, and maybe we can have some collaboration later. Actually, Professor Wang has already introduced some of the machine learning methods, and so here I want to talk about something about the phase transitions. Okay. Now we know that in our daily life, actually there are many things that will change. Okay. Especially, like for a very common example is water. Right? Water freezes into ice, or if you increase the temperature, it can become steam. Right? There's a change, a sudden change of behavior. Okay. It can be from a liquid form to a solid, or from liquid form to a gas. There's a sudden change in the behavior. So, and there are many other things. They have phase transitions like metal. Metal actually, if you change the temperature, some of the metal will have magnetic behavior. But if the temperature is too high, the behavior will be destroyed. The magnetism will be destroyed. And there are other things like climates, right? Our climate will also change, depends on the temperature, the average temperature. Okay, nowadays, well, we know we have global warming, and the temperature, up to some temperature, maybe there's sudden change. There's phase transition, and then the whole climate will have a disastrous change. Okay, and even for something like traffic jams. Okay, when there's, I think in the downtown area of Jakarta, maybe at certain time, there is too many cars in the street, right? And then suddenly everything jammed out, okay? That is also a phase transition. It can be discussed in the similar ways. Okay. Now, some of the transition is very obvious. I mean, obvious is very easy to identify, but some of them are not. Like magnetic and magnet, I just mentioned before, it becomes magnetic, but you can, when you look at the magnet, it doesn't seem any change in the appearance, right? But its properties has changed suddenly. Okay? Like the figure I show here is a superconductor. Okay? At very, very low temperature, this cube of material, it is still a cube. Okay? It doesn't look any, there's no difference in the appearance, but it becomes a superconductor. Because when you the resistance drops to zero, okay, and it has some special magnetic. They have some special magnetic behavior, like this one. It looks like it can anti-gravity, right? So there are some changes are not easy to identify. Okay. Now, so is there any way to identify this hidden change? Usually, in physics, we will use we will identify this matter with a quantity we call order parameters. Order parameters identify that the material is in a state of order state, or it is not, or it is in a disorder state. Okay, and usually we hope that this order parameter is easy to measure. Okay, but that works in some cases, but not all the cases, because in some cases the change is more subtle. You don't know how to define that parameter. Okay. Now, as Professor Wang just tell us, that actually machine learning is very good at looking at patterns, right? If you tell the machine which pattern corresponds to what states, okay, you give a lot of data to the machine, then at some point it can learn how to identify these patterns, whether it is a cat or it is a duck, or it is a disease or it is not, right? So machine learning is very good at this. Okay. It can be a good pattern detector, and so maybe we are asking, maybe for something very difficult, for some hidden patterns, maybe a machine can help us to identify the those order or disorder. Let me first introduce a common, very simple model, physical model. Maybe some of you already know that because it's very simple and it has very wide range of applications, even in economic or finance. This is the Ising model. Like in a 2D lattice, it has two states. In physics, we usually identify this state as spin up or spin down. Well, or it can be 0 or 1. It doesn't really matter. But it's just binary. It has two states. Okay. Now, and these spins interact with each other. For example, they can prefer a line parallel. They're pointing to the same direction with its neighbors. Okay. So at certain temperature, when we tune the temperature, the behavior will change according to some statistical physical laws. Okay, so they will the arrangement will be different. Like for high temperature, you look at the left one, the right figure here. At very high temperatures, those spins will behave randomly. Okay, they will randomly become up or down. The interaction becomes not very important. Okay, the thermal fluctuation becomes more important. So then they are randomly distributed. So there's no pattern, no special pattern here. Okay, and this pattern also this configuration will change actually as because we are at high temperature. It will randomly fluctuate. Okay, but when we reduce the temperature at certain points, because the thermal fluctuation is not large enough, then the interaction becomes very important. So these spins try to align into the same direction, maybe spin up or spin down, so you can see a uniform pattern, right? So at some point, in the temperature, we call it Tc, there was a certain change here. So there's a phase transition. We use this, in physics, we use this model to describe those phase transition in magnets. Okay, it's very successful and it can be applied to other things, not just magnetism. Okay. So now, can we use machine learning to detect this phase transition? The simplest thing is just like what have been introduced by Professor Wang. We can label these states like for those order states, we give it a label like 0, and for other disorder phase, we give it a label 1. Okay. So we just tell the machine or the model that there are two phases. One looks like that, the other phase looks like that. Okay, and then you give the model a lot of data, and somehow we hope we wish the machine learn how to identify these states. Okay, and this is very simple actually. Okay, because it has only 2 states, and we can successfully, very easily to train the machine to learn these 2 phases. But actually, this is not very useful because you already know the answer. You already know that which phase is order or 1, right? And then why do you ask the machine to do this for you? Because you already labeled them. Okay, so there's no new discovery here. Okay. So we want to go further ahead, and we use the so-called unsupervised learning. That is, we don't want to give the machine the labels. Okay, and we hope the machine to try to learn the information from the data itself. Okay, so so what can we do that? Well, how can we achieve this? We use a convolution autoencoder here. I will skip all the technical details here. Okay, there's many layers of neural networks, but the detail I will just leave it here. But just like if we have initially we have a lattice configuration like this. Okay, now this actually this so-called autoencoder, it will try to compress the image into a much smaller size. Okay, and then decompress, it becomes the original size. Okay, but of course, because we compress this lattice size, we are sure that there's some information of this original pattern is lost, right? Because the size is much smaller. It has lost some information, just like those pictures. We compress a picture, then we try to decompress it. We have to lose some information. So the resulted lattice may look like this. It's not as clear as the previous one, right? Well, kind of, we still recognize the shape, similar shape, but it's not so sharp, right? Because it lost some information. Okay. Now, in these networks, what we do is try to we train this network so that the resulted picture is as close as the previous picture. Okay, that means we actually subtract these 2. Okay, and we hope that the reconstruction error is as small as possible. Okay, we try to retrain the parameters inside that so that the information loss is as less as possible. Okay, but of course it cannot become 0 because this is an encoder, so it must have some information loss. Okay, so our training, but I have to emphasize that in the training there's no labels. Okay, you don't have to manually put on the labels. You just give all the data to the model, and it would try to do the minimizations itself. Okay, so we hope that it can distinguish normal order phase or disorder phase. Now here is the results. This MSE is the reconstruction error. Okay, so we try to minimize it, but for different temperature, okay, this MSE is different. So like for high temperature, the disorder states, this error is very large, or relative to the order states. Okay, the reason is very simple, because this phase is already very disordered. You try to reconstruct it, but it has no special pattern. Okay, so it's quite difficult to reconstruct this pattern. But for this one, it's almost the same, right? Every place is almost the same, has the same sign. So to reconstruct this, it's very simple. So the error is relatively small. Okay, so we have this trend. Okay, so as we increase the temperature. Now you can see, so for the disorder phase, the MS is larger, and this for the order phase, this is much smaller. Okay, so there's some kind of the real phase transition occurs here, right, in between of these two phases. Well, from this result, you can kind of tell that oh, there's a phase transition, but you cannot really exactly pinpoint the position of this TC, right? So it's not very helpful, it seems. But if you look at the variance, if we look at the variance, that means the variance of each temperature, okay, and there's a very significant change around TC. Okay. Now this part is just the variance, the error bar of each data point here. Okay. So you can see that. Of course, I have times the L. The L is the lattice size. Okay, so that different size of data will collapse into the same curve. Okay, but essentially it's the variance or the fluctuation of the data. Okay, we can see that there's a sharp peak here. Okay, right. So here, so at this transition point, we know that it's clear that this our model can identify these two phases very clearly, right? Okay. So and we repeat this approach for different sizes. So and we plot and we do a scaling, and for infinite size it will extrapolate to the exact, or very close to the exact TC, theoretical TC of this model. Okay. Wow. So it seems our unsupervised learning model is very successful on this Ising model. But Ising model is the simplest one of all these statistical models, right? Can we do a more complicated thing? So next step, we try to look at the so-called Q-state clock model, which is just a generalization of the Ising model. For Ising model, just as I just told you, that it has only two states, right? Spin up and spin down. But you can generalize it. Like maybe you have three states pointing to different positions, equally or uniformly distributed, right? Pointing up and then 120 degree and 240 degree, right? Like this is, then it becomes, the Q means how many states you have. If Q equal to 3, you have three different possible. And if Q equal to 4, it was not like that, right? You have 4 possibilities. And this is Q equal to 6, and this is Q equal to 8. All right, and here I just show you how does it look for Q equal to 9. Okay, it's very complicated, and for high temperature, it still looks very random, right? All the fluctuations, and for low temperature, they all try to pointing to the same direction. But in between, there's something very strange. Okay, it's kind of irregular, random, but still there's some, looks like there's some pattern here. it's difficult to tell what is it, okay? But it looks like there's some pattern, but it's not easy to identify. Actually, these phases, we call it BKT phases. There's some vortices inside these phases. And there's anti-vortex and vortex combination and recombination inside. We call this topological phase. Then, then we try to use the same model, machine learning model, to see whether it can identify these phases automatically. Again, we do not label this data. Okay, we just train the model with the original configurations. Okay. Now here is the results. Like for Q equal to 3, we have 3 possible states, and there's only one, and there's a sharp peak here. This is again the fluctuation of the reconstruction error. Okay, and in this case, it's quite similar to the Ising model, right? There's a sharp peak. Okay, and for different lattice size, and we reconstruct. I mean, they are overlap on the same curve, and we can do a size scaling. It just pointing to the exact, very close to the exact TC here. Okay, but for like Q equal to 6, actually for Q equal to 5 or larger than 5, there's something special happens here. You see, there are 2 peaks. Okay, that means there are 2 phase transitions. Okay. And in between, this is the phase I just told you that there are BKT phases, the topological phases. Okay. And but we didn't tell the model, our machine learning, there are 2 phases. Okay, or there are 1 phases, or there are 1 phase or 2 phases. It automatically identifies the phases here, or the transition. Of course, the machine doesn't know what it is doing. It just analyzes or try to minimize the reconstruction error, and then it extracts information from our data. And turns out it can successfully identify these 2 transition points. And if we do the scaling again for different, because this phase has different size scaling, so we use different formula to scale them, and they also give the very precise critical temperature. And actually, this work has been published a few years ago. This is my colleagues. Okay, so this is we call it anomalous detection, and in fact, there is some reason behind it for the successful of this method, because the error variance actually corresponds to the susceptibility. So usually at the transition point, the susceptibility will goes to infinity, and we also show that it obeys the finite size scaling, and at least up to now, it applies to these 2 different models. Actually, we have tried others more complex statistical model, and still it can apply. It can successfully identify the transitions. Okay. Wow. There's some more detail. It's more technical, so I may skip here. Actually, we also argue that our approach can distinguish the first order transition, whether it's first order transition or is continuous transition, it's a PKT or some other different kind of transition, because the scale is different for all these. Okay. So, so although the data is more complex than before, and but in fact, from our approach, you can still extract some information. Okay, but of course, we do not know what is the order parameter of the system. But still, we can extract information so that we know at which temperature that the information or the fluctuation change. Okay, but this is still very helpful in some cases. Now, in our previous model, I just tell you I changed the temperature. But in other cases, you may change other, the transition may happen due to different magnetic field or pressure or other things. So there's many possibilities that this model can apply. And maybe in the future, we can look at some quantum system. The one I just introduced is on classical system. And it may also apply to some experimental patterns because we can have some experimental data show different configuration of some materials. Okay, and how can we define or how can we find out there's certain change in those patterns? We can use the similar method. Okay, and of course the system I introduced to you is. We already know that the phase diagram, how does it behave, but we can apply this our model to other different systems, which we may not know the real phase diagram. Okay. Okay. I think I will stop here, and if you have any question or if you are interested to later topics, we can talk about later. Thank you very much for your attention.
Thank you very much, Professor. And then, yeah, it's very interesting that we learn about the application of the machine learning by knowing the phase transition of the materials. So I would like to open question again. So we will have 3 questions from the audience. So if you have questions, please raise your hand. Or probably from investor, Professor, is okay?
Yeah.
So yeah, so I have experience measuring the two pieces,
Yeah.
solid and liquid.
Yes.
The liquid is water,
Yes.
and the solid is 2 metals. One is aluminum, the second one is copper. Then we measure that metal separation during vibration. And then we measure the electrical conductivity among 3 materials, water, aluminum, and copper. But the problem is the electrical conductivity, water is very low, and then both of metal is very high, and then the difference is very small. Then it's quite difficult to distinguish between aluminum or copper. So is it possible to use the model that you explained to us? What's the challenge for that?
Yeah. What kind of data you have? Yeah.
Electrical conductivity.
Conductivity.
Yes.
So you say, okay, these 2 metals, their conductivity is very similar, and you try to distinguish them.
Yeah, I would like to distinguish.
Yeah. Okay. Well, the model I introduced, of course, depends on the pattern. Okay, it's an image. Okay. But of course, this can extend to other things. If you have a list of data, but it's just one conductivity, I don't think it's enough. Maybe you need more features. Okay. Yeah, maybe other physical temperature. Yeah, other physical properties. Then it will be easier to separate them.
So I'd like to say, is it possible if we put a camera top of the vibration deck, then since we can see that aluminum and copper is different color, is it possible?
Or if you have different colors, then you can you can distinguish it visually, right? It's too simple.
Yeah, since we would like to know the automation.
Yes, of course. Yeah, it's possible. Then it's like you look at, transform into numbers, right? Then it's frequency of the optical frequency. Yeah.
Then you want to know the boundary. Yeah.
Then it's quite easy. Yeah, it's quite easy.
I see.
Yeah.
So
That is quite easy. Yeah.
Thank you. For
Yeah,
the answer.
Okay.
So I'd like to open another question from the audience.
Actually, it's quite theoretical. I know that.
Yeah.
I have some card maybe to share with you.
Some
card.
postcard. Yeah.
Postcard. Yeah.
Thank you.
Because we are from the science college, so this postcard is posed for scientists. Okay, one is in physics, one is in chemistry, one is in life science, and the other is mathematics. Yeah. These four are very famous. Okay. Thank you. Oh, yes. And this one too.
Oh, yes. Good. Yeah. Thank you.
Okay, Dr. Yevgeny Fauzan, please. Sorry, since there's no one, so yes, please.
Yeah, Professor, I would like to ask some question, maybe rather theoretical. You show easy model in the first part of your presentation, and you show some data with TC, the temperature.
You mean the temperature of the TC?
Yeah. I'm wondering how you determine the TC, because from the data it seems there is nothing special with the TC in your data. And you claim that your TC is close to the experimental, so I'm wondering how you determine the TC.
It's not close to the experimental result. It's close to theoretical results. Yeah, the easy model can be solved analytically, so it has analytical results. Yeah, but actually, of course, many materials have similar behavior. Of course, the easy model, of course, is the ideal case. So in real materials, of course, you may have some other factors you have to take into account. Maybe so you change the TC or the different a little bit, yeah, something like that. But here I just show you some theoretical results. Yeah.
I did first principle calculation for
Yes.
Gas and solid phase.
Yes.
So maybe I'd love to hear your lecture about quantum Monte Carlo.
Yes.
That you show in your last slide.
Okay.
If there's any occasion, maybe I'd love to hear your.
Okay. Quantum Monte Carlo results will be a little bit different. We tried a little bit. We have not finished yet because it's no longer a two-dimensional pattern. It has an imaginary time, so it's a three-dimensional thing. Yeah. So I have not put anything here because I thought it's too technical. Okay. But it's possible to apply to this system, to the quantum system also. Actually, there's many other machine learning methods that try to do the similar thing. But also, actually, I think the method I introduced is kind of the most simplest one. Then some more complicated, maybe they need to calculate you have to do some calculation before you input the data. Yeah, sometimes you need to calculate the number of vortices or the structure of the vectors before you input into the machine learning. Yeah. But here we just use raw data. We don't assume anything and just put the original image in the machine learning, that it will identify the phase changes. Yeah. Yeah, we can talk about this later. Very interesting. Yeah. Thank you. Thank you for your question.
Okay, thank you, Dr. Lee. So one more, if you have, yeah, Dr. Budi, please ask the question.
Thank you very much. I want to ask in the context of the gradual sensor drift, machine learning is often used to monitor and analyze long-term measurement pattern. So how can machine learning method distinguish between natural system variation and change caused by sensor degradation? Sensor drift, how the measurement and sensor drift, and how to optimize machine learning, how to condition.
You mean the optimization?
Yeah.
Of the machine learning?
For the machine learning.
In my case, it's very simple. You just minimize the reconstruction
error. We try to reconstruct the same pattern as before. But of course, it will not be perfect because we compress it. Okay. So I think Professor Wang has already introduced how the optimization works. We use the usual difference descents to optimize the network. Yeah. Okay. Do I answer your question? I'm not sure.
Okay. Yeah, I mean the sensor sometimes to make the long time in the
Yes.
degradation or maybe material underground. How to make the maybe calibration for the machine learning. By machine learning, I think there maybe domain adaptation or machine learning conventional. How to make the long time under different device maybe for the context measurement.
You mean for the sensor?
Yeah, maybe I can try to think about your problem. If I have a car, I drive for 10 years, yeah, the behavior are different. So there are different cars, yeah. But actually, we always use the same controller, okay, same engine, yeah. So maybe we can think about if initially you have a model for them, okay, and you know the model's type, yeah. But maybe as you say, the sensor is decayed, so the coefficient is not correct. Then the model is incorrect, the coefficient. So as I mentioned, you can use that. So PN, the idea, yeah, physical environment, you know, you can assume the parameters are known, and then you feed in the data to train the neural network to capture those parameters. So you will have a new model for your new sensor, and based on that, you can adjust that. Because you can redo the mapping, yeah, for the correct value for the sensor. So you can recover some, not many. Okay, you can try. It's quite interesting to use PIN to do it. Really, yeah. Because each thing is model from physically or from mathematically. We can use a model to represent that. Except our mental. And we don't have model version.
Thank you very much.
Okay, thank you, everybody. And I think we will have one more question. Okay, yeah. So from Dr. Rashid. So please.
Okay, thank you very much. I would like to ask about you, Professor.
Yes.
Yeah, actually, my recent interest is in cybersecurity. But I had a chance 14 years ago study about the chaotic theory.
Chaotic theory.
Yeah.
Yes.
And when I saw your slides about the phase transition,
yes,
and then the Q state, I remember about the chaotic bifurcation. I think it's similar, right?
Yes.
From the first bifurcation, second bifurcation, then quarter bifurcation, and so on. And
Yes,
then
yes.
become the chaos, right?
Right.
And is your models can apply to the transition of bifurcation, chaotic bifurcation? I think this, chaotic theory is about the nature, right?
Yeah.
So I think it's very similar.
Yeah.
You can find many chaotic attractor in many models. And we can visualize the first bifurcation, second bifurcation.
Actually, it's possible. You can transfer both and no function. Maybe it's possible. Because we need to minimize some energy, yeah. So the mechanism. We call about that the function called L, which we call loss. But if you can add the sum function inside, because you talk about the chaotic, yeah, maybe we can measure some phase change, yeah, and add it in, and use neural network can solve that kind of problem, I believe. Because some people already do it for circular motion, yeah. Okay, they try to use the neural network to approach it. Okay, so if you are talking about if there's a real system, we have lots of measurement data, and then we quite come back to use neural network to find approximation. And based on that, we can try to determine what kind of function we need to make in order to detect the behavior. Once the function is controlled, maybe you can detect the phase for chaotic change. Yeah, maybe it's possible. I think many people will be doing this.
Yeah, I think it's interesting. Okay, thank you very much.
Thank you.
Thank you very much. So it's very, very insightful and yeah, give us many, many benefits from you for the machine learning. I think yeah, this is almost the end of today's event. We still have 3 small mini events. So the next one is the souvenir from our head of department, and then the next one is a photo session, and then the last one. So we would like to invite professors to one of our lab with about AI. So, okay, thank you. So I would like to please the head of department, Dr. Yuris, to come to the front and give the souvenir. We also would like to take a photo. Okay, thank you very much. So I would like to close today's event, but the last, before I close, we would like to invite all of the audience. Yeah, so I'd like to ask all of the audience to stay in your own desk, and we would like to take a photo together.
Fotonya dari sini, tak matiin ya.
So I think we need to go to the center since the camera cannot capture all of us. Thank you everyone for attending today's event. So see you again in the next one. Thank you.